Unit 3 Stability of Earth Slopes. The soil slopes may be either man-made or natural. The examples for man-made slopes are cuts and fills for highways and railway lines, canal banks, and temporary excavations. The examples for natural slopes are stream banks, hillsides, etc. A slope failure occurs when the forces causing failure are greater than the shearing resistance developed along a critical surface of failure. There are various causes of failure of slopes. The main reasons are due to increase in shear stresses or decrease in shear strength. The important causes of failure of slopes are gravitational force, force due to seepage water, erosion of the surface of slopes due to flowing water, the sudden lowering of water adjacent to a slope, and forces due to earthquakes. That first one is gravitational force. The most important force that causes the movement of soil is the component of gravity that acts in the direction of probable motion. The second one is force due to seepage water. The seepage occurring within a soil mass causes seepage forces which have a greater effect on the stability of a slope as the seepage pressure decreases the shear strength of soil. Third one is erosion of the surface of slopes due to flowing water. Erosion of the surface of slope may be the cause of the removal of a certain amount of soil and may thus lead to an increased instability as far as mass movement is concerned. Erosion in the form of undercutting at the toe may increase the height of the slope or decrease the length of the incipient failure surface, thus decreasing the stability. Fourth one is the sudden lowering of water adjacent to a slope. When there is a lowering of groundwater or free water adjacent to the slope, there is a decrease in the buoyancy of the soil, which is in effect an increase in the weight. This increase in weight causes increase in the shearing stresses. Then fifth one is forces due to earthquakes. The earthquake force decreases the intergranular pressure and increases the neutral pressure. The entire soil mass may flow like a liquid, which is called liquefaction. Types of slopes. There are two types of slopes, infinite or finite. Infinite slope is large in extent, theoretically infinite, and the properties of soil will be same at identical depths so that the slip surface will be a plane parallel to the surface of slope. Finite slope is limited in extent and the properties of soil will not be the same at identical depths so that the slip surface will be curved. Types of slope failures. First one is rotational failure. When failure occurs by a mass of soil sliding along a curved surface of rupture, it is called a rotational failure. There are three types of rotational failure: toe failure, slope failure, and base failure, depending on the location of weak stratum. If the weak stratum is located at the toe level, then the failure surface passes through the toe. This kind of failure is called as toe failure. If the weak stratum is located above the toe level, then there is a possibility of slope failure. And if the weak stratum is located below the toe point, then the slip surface passes below the toe. So in this case, base failure occurs. Second one is translational failure. Translational failure occurs in infinite slopes where the failure surface is parallel to the slope. A sheet of soil moves as a mass down the slope. Compound failure. It is a combination of rotational and translational failures. A compound failure surface is curved at the two ends and plane in the middle portion. A compound failure occurs when a hard stratum exists at considerable depth below the toe. Wedge failure. A failure along an inclined plane is known as wedge failure. It occurs when distinct wedges of soil mass become separated by cracks, joints, etc. This failure is similar to translational failure but may occur in infinite slopes also. Definitions of factor of safety. There are three definitions of factor of safety depending on the type of soil. First one is factor of safety with respect to shear strength, represented with symbol F suffix S. which is equal to ultimate shear strength divided by mobilized shear strength. So this is equal to C plus sigma dash tan phi divided by Cm plus sigma dash tan phi. So here Cm and phi m are called as mobilized cohesion and mobilized angle of shear and resistance respectively. If the soil is purely cozy soil where phi equal to 0, in that case these terms will become 0, so that the factor of safety with respect to cohesion equal to C by Cm. If the soil is granular soil where C equal to 0, then the factor of safety with respect to friction equal to tan phi by tan phi m. The stability of finite slopes can be analyzed using various methods such as Swedish circle method, friction circle method, by using Taylor stability number and Bishop's method. Swedish circle method is given for two cases, purely cozy soil and cozy soil. If it is a purely cozy soil where phi equal to 0, then the factor of safety with respect to sliding is given as the ratio of resisting moment to the driving moment. So suppose this is the slope and AD is the failure surface, and this failure surface, since it is like arc of a circle, it will be having one center, so it is point O and its radius is R. The angle subtended at point O is delta. The weight of the sliding soil mass, this is the sliding soil mass, the weight of the sliding soil mass is W, which is acting at a distance of x bar from point O. So here, which are all the forces resisting sliding and which are all the forces driving the sliding. So here the driving force is W and the resisting force is cohesion. Since it is purely cozy soil, only cohesion will offer resistance against sliding. So for taking the resisting moment, we have to take the resisting forces. So here cohesion is the only force that is resisting the sliding. So cohesion, because it is given as a pressure, we have to multiply with the arc length to convert into force. So Cu into arc length, because it is acting along the arc, we have to multiply with the arc length multiplied by perpendicular distance. We have to take the moments about point O. So perpendicular distance is R. So this is the resisting moment. And driving moment, here weight of the soil is causing driving. So its moment with respect to point O is W into x bar. Then by taking the ratio of resisting moment by driving moment, we will be getting the factor of safety as Cu into arc length divided by W into x bar. So arc length we can find using the equation pi r delta by 180. If it is a cozy soil where both cohesion and friction are there, then the Swedish method for C5 soil is called as method of slices. So here first we have to draw the slope to some scale. Then we have to locate the center of slip circle. Then we have to draw the slip surface. Then this sliding soil mass has to be divided into n number of slices. And for each slice we have to draw the center lines. So here we have to divide the sliding soil mass into n number of slices. Say about 6 to 10 slices. Then for each slice we have to draw the center lines. Then we have to assume that the weights are acting along these center lines. Weights of different slices have to be drawn as verticals through the center lines of slices. So they are represented as W1, W2, W3, etc. Then we have to draw normal and tangential components for all the slices, and we have to represent them as N1, T1, N2, T2, etc. Then here we have to identify what are all the forces causing the failure and what are all the forces resisting the failure. So here driving forces are nothing but the tangential components. So tangential, sum of these tangential components have to be taken, and then when we take the moment about point O, we will be getting the driving moment. So here perpendicular distance is R. Then resisting moment. Here because it is the C5 soil, both cohesion and friction will contribute towards resisting the sliding, because shear strength of coarser soil or seafloor soil is C plus sigma tan phi. So C plus sigma tan phi. Here sigma is nothing but sigma n. So sigma n tan phi. For that, when we take the moment about point O, we have to multiply with R. Then for the cohesive force is C into arc length multiplied by perpendicular distance R. We'll be getting the resisting moment with respect to point O. Then we can take the factor of safety as the ratio of resisting moment by driving moment, which is equal to C into arc length plus tan phi into sigma n divided by sigma t. So everywhere R is there, that will get cancelled. So that will be getting the equation like this. So here we need the sum of normal and tangential components. So these two values can be obtained either by creating a tabular column or by preparing the N and T curves. So how to prepare this N and T curves? For that, we have to draw a horizontal like this, and then we have to plot the values of normal components as ordinates with respect to each slice, and then we have to join these ordinates with a smooth curve, so that we will be getting the N curve. Now we have to use the planimeter to find the area of this N curve, so which is nothing but sigma n. Similarly, we have to plot the T curve by taking the values of tangential components as ordinates, and then by finding the area, we will be finding the sigma t value. So here if the theta value, if it is plotting on the left side of vertical, we should take it as negative. In that case, tangential component is also negative. So then we can substitute in the equation and then we can find. Another method is by using the tabular column like this. So here we should write the slice number, and for each slice we have to write the width and mid-ordinate. Mid-ordinate is nothing but the height of center line of the slice, this one. Then we have to find the weight of slice. Weight of slice equal to volume of slice multiplied by unit weight of soil. So how to find the volume of slice? For that we have to multiply the width with mid-ordinate, and we can take the unit thickness. Then we have to multiply with the unit weight of soil to get the weight of slice. Then theta values, if they are plotting on the left side of vertical, we should take it as negative. If they are plotting on the right side of vertical, we should take it as positive. Then normal component equal to W cos theta and tangential component equal to W sin theta. Then we can find the sum of normal components and sum of tangential components. Then we can substitute in the equation of factor of safety, and then we can estimate the factor of safety. Suppose if the slope is submerged, then we should take the water force also into the equation, where we have to deduct this water force from the normal components. Fellenius method. This method is given only to locate the center of critical slip circle. So here, suppose this is the PQ is the slope. Then there is a table given by Fellenius with respect to different slopes. He has given the values of alpha and beta in the form of a table. So depending on the slope of the embankment, we have to find the angles alpha and beta from the table. Then we have to draw a line with an angle alpha with the slope and another line with an angle beta with horizontal. So these two lines will intersect at a point. Say it is point A. Then we have to locate point B, which is at a depth of h below point P and at a horizontal distance of 4.5 times of h, so that we can locate point B. This h is nothing but height of the slope. This is the h. Then we have to join the points A and B with a straight line, and then we have to extend it backwards. Now we have to mark 3 points O1, O2, O3 on this extended line, and we have to assume that these are the trial slip centers. Initially, by taking O1 as the center, we can take this O1P as the radius, and then we can draw the slip surface. Then we can use the method of slices to estimate the factor of safety, and this factor of safety value has to be plotted as ordinate with respect to point O1. Here we have to plot the factor of safety value to some scale on this line. Then we have to take O2 as radius, and by taking O2P as radius, and we can draw the slip surface, and using the method of slices we have to find the factor of safety, and that value has to be plotted as ordinate. Similarly, we have to repeat the procedure once again by taking O3 as center and performing the method of slices. We will be getting the factor of safety. Then by joining these three ordinates with a smooth curve, we will be getting the curve of factor of safety. For this curve, we have to find the lowest point, and for that lowest point, we have to draw one perpendicular onto this extended line, so that we will be finding the critical slip circle. So this O1, O2, O3 are trial slip circles. So by finding this lowest point, we can find the critical slip circle. Then by taking this critical slip circle as the center, and by taking this OP as radius, we can perform the method of slices once again, and then we can find the factor of safety. So that is the method which we have to use for finding the factor of safety when the soil is coarse soil, where both C and phi are there. Suppose if it is purely coarse soil where phi equal to 0, then this point itself is the center of critical slip circle. There is one example. An embankment 6 meter high has a slope of 1 vertical to 2 horizontal. The material of slope has C equal to 5 kPa, phi equal to 30 degrees, gamma equal to 19 kilonewton per meter cube. A trial slip circle has a radius of 8.8 meter and its center is at the same level as the top of the embankment. The slip circle passes through the toe. By the method of slices, find the factor of safety of the slope with respect to this slip circle. So here, height of the embankment is given as 6 meter and slope is given as 1 vertical to 2 horizontal. So when the vertical is 6 meter, horizontal will be double of this, that is 12 meter. So we have to locate one point as the toe of the embankment. Then we should take 12 centimeter horizontally and 6 centimeter vertically, so that we can locate the top of the embankment. Then we have to join these 2 points with a straight line, and we have to draw a horizontal representing the top of the embankment. So here, how to locate the center of slip circle? So after locating the center of slip circle only, we can draw the slip surface. So to locate this center of slip circle, here one hint is given. The hint is center is at the same level as the top of the embankment. So we know that the center is along this line, top of the embankment. So we have to draw one dotted line, and then by taking the radius of 8.8 meter from the 2 point, we can locate the center O. Then by taking the center and radius 8.8 meter, we can draw the slip surface. So that we will be getting the other end of the slip surface. Then we have to join these two endpoints of the slip surface to point O, so that we can find the included angle at point O. Angle subtended at point O, which is represented as delta, has to be estimated from the graph. Then we have to prepare a tabular column like this. So we have to divide the sliding soil mass into n number of slices. So here each slice is taken as 2 centimeter. The last one is a little smaller. It may be little smaller or it may be little bigger. Then for each slice we have to draw the center lines, and we have to represent the weights of slices as W1, W2, W3, etc. Then we have to draw the normal components for each slices. We can align the scale between point O and this intersection point, and then we can extend it so that we can draw the normal components. Then we have to measure the angles between this normal and vertical, normal and vertical. There are theta 1, theta 2, etc. So here in the table, first we have to write the width of the slice, then mid-ordinate. Mid-ordinate is nothing but height of center line. For each slice, we have to measure the height of center line of that particular slice. That is taken as mid-ordinate. Then volume, by taking the unit thickness, we can find the volume. That is nothing but product of width and mid-ordinate. Then we have to multiply with the unit weight of soil to get the weight of the slice. Then because here the value is plotting on the left side of vertical, we have taken as negative. Then normal component equal to W cos theta and tangential component equal to W sin theta. Since the theta value is negative, tangential component is negative. Then if the value is plotting on the right side, we will be getting the theta value as positive, where both normal and tangential components are positive. So after calculating the normal and tangential components for all the slices, we have to find the sum of normal components and sum of tangential components. Then we have to substitute in the equation of factor of safety to estimate the factor of safety. So C value is given, arc length we can calculate using the equation pi r delta by 180. Tan phi value will be given. Sigma n and sigma t values will be obtained from the tabular calculation. So if you take a different width, you will be getting different values of normal and tangential components, and the procedure is same. We will be getting the factor of safety by taking this equation, where we have to substitute the sum of normal and tangential components which are obtained from the tabular calculation. Another example is, determine the factor of safety for a slope of 40 degrees in a purely coarse soil using method of slices. The height of slope is 5 meter, C equal to 30 kPa, gamma equal to 16 kN per meter cube. The trial slip circle is located by Fellini's angles, alpha equal to 26 degrees and beta equal to 35 degrees. So here hint is not given to locate the center of slip circle, but the Fellini's angles are given. So using these angles, we can locate the center of slip circle. And one more thing is, here it is mentioned that the soil is purely corrosive soil. So for purely corrosive soil, the equation for factor of safety is Cu into R into arc length divided by W into X bar. So Cu value is given, cohesion value is given, then arc length. So to find the arc length, we need delta value. So that is not given. Then W value, X bar value are also not available. So we have to find all these values from the method of slices. So we have to use the method of slices here. So for that, first we have to draw the slope to some scale. So here height of the slope is given as 5 meter and slope angle is given. So by taking the 2 point and angle 40 degrees, we can draw the slope. So at 5 meters height, we have to draw one horizontal representing the top of the embankment. Then here Fellini's angles are given. So we have to take 26 degrees with respect to the slope and 35 degrees with respect to horizontal. So these two lines will intersect at point O. So from this point, we have to measure the distance between this 2 point and point O. And we should take it as R. So from this graph, we can find the radius R. Then by taking this radius, we have to draw the slip surface by taking O as center and R as radius. This distance between the center and 2 point. We can draw the slip surface. Then from this end point, we have to draw another line to point O, and the angle between these two lines joining the endpoints of the slip surface, we can measure the delta value. So this is nothing but delta. Then after finding the delta and R values, then we have to divide this sliding soil mass into n number of slices. To find the W and X bar values, we have to use the method of slices now, for which we have to divide the sliding soil mass into n number of slices. For each slice, we have to draw the center lines and then we have to represent the weights as W1, W2, W3, etc. But here we need not draw the normal and tangential components, because in the equation Cu into R into arc length by W into X bar, we don't need sum of normal components and sum of tangential components. So we need not draw normal and tangential components in the graph. We just have to find only the W1, W2, W3, etc. Then the distances. Here we need the location of total weight of sliding soil mass. So we have to find the X value with respect to point O. That is the reason for each slice we have to take the horizontal distance. Horizontal distance between the center of the particular slice and point O. So those values have to be taken as x1, x2, x3, etc. So if that value is coming on the left side of point O, we should take it as negative, and if it is coming on the right side like x3, x4, etc., we should take it as positive. So here we have to write the width of slice, then mid-ordinate is nothing but height of center line, then weight of slice equal to width into mid-ordinate into unit weight of soil. We are taking the unit thickness here. Then X value, that is the center of that particular slice with respect to point O. Horizontal distance between point O and center of that particular slice. If it is coming on the left side, take it as negative. If it is on the right side, take it as positive. Then we have to find the product W and X. Then we have to calculate the sum of weights of all the slices and sum of Wx. So then we can find the X bar value, which is equal to sigma Wx by sigma W. Then we have to calculate the arc length, which is equal to pi r delta by 180. So here R value and delta value are obtained from the graph. Then here W and X bar values are obtained from the tabular calculation. So by substituting in the equation, we can estimate the factor of safety. Another example is an embankment has a slope of 1.5 horizontal to 1 vertical with a height of 9 meter, and the soil properties are C equal to 25 kPa, phi equal to 20 degrees, gamma equal to 18 kilonewton per meter cube. Determine the factor of safety for a trial slip circle passing through the toe. The felonious directional angles are alpha equal to 26 degrees and beta equal to 35 degrees. Use method of slices. So here also height is given, that is 9 meter, and slope is given as 1.5 horizontal to 1 vertical. Vertical is 9 meter, so horizontal will be 1.5 into 9. So by taking those dimensions of 9 meter and 1.5 times of 9, we can locate the other end of the slope, so that we can draw the slope, and then one horizontal representing the top of the embankment. Then here felonious angles are given, alpha and beta. So by taking alpha with respect to slope and beta with respect to top of the with respect to horizontal, we can draw two lines. Those two lines will intersect at a particular point, that is the center of slip circle, and we can measure the R value from the graph by taking the distance between O and A. Then by taking O as center and R as radius, we can draw the slip surface. After getting the other end of the slip surface, then we have to draw a line to the point O, so that we can measure the value delta. So this R value and delta value are obtained from the graphical construction. Then we have to find the arc length, which is equal to pi r delta by 180. Then to estimate the factor of safety, we should know the normal and tangential components. So for which we have to construct the tabular column. So in the tabular column, we have to write the width, the mid-ordinate, volume, weight, theta, normal and tangential components of all the slices. And we have to find the sum of normal and tangential components. Then we have to substitute in the equation of factor of safety to estimate the factor of safety. Here the sum of normal components and sum of tangential components and sum of water forces are also given. So since the water force is given, we have to deduct the water force from the normal components. Since it is a submerged slope, we have to deduct the water force from the normal components. And to estimate the arc length, we have to use the equation pi r delta by 180. Here all the values are given, r value is given, delta value is given, so that we can estimate the arc length. And using this equation, we can estimate the factor of safety. So here in this problem, one figure is given representing the total weight and its location also with respect to point O. Delta value is also given, height of the slope is given. So here the soil is purely coastal soil because phi equal to 0. So for purely coastal soil, the factor of safety equation is Cu into arc length into R divided by Wx bar. So in this equation, Cu value cohesion is given as 55 kPa. Arc length, to find the arc length, we have to use the equation pi r delta by 180. Delta value is given as 64.5 degrees and R value is given as 19 meter. So by substituting these values, we can calculate the arc length. Then divided by W. W value is given as 2050 kilonewton. X bar value is given as 9 meter. So by substituting all the values in the equation, we can estimate the factor of safety. Here in this problem, the slope is given, C value, phi value, saturated unit weight, all the values are given, Pellinus angles are given. But here one condition is there, that is when the canal is running full. That means the slope is submerged. When the slope is submerged, we should take the submerged unit weight to estimate the weight of soil. So as usual, we have to do the graphical construction with the given height of the slope and slope angle. Then we have to divide the sliding soil mass into n number of slices. So for each slice, we have to find the width, then mid-ordinate, then volume, weight. But while calculating the weight, we should take the submerged unit weight. So saturated unit weight minus unit weight of water. So 19.81 minus 9.81. So we have to use the submerged unit weight of 10 kilonewton per meter cube in this equation, and then we have to estimate the weight of soil. So since we are taking the effective weight, we will be getting the normal and tangential components as effective values. After finding the sum of normal and tangential components, we can substitute in the equation and then we can calculate the factor of safety.